This is the last class on linear algebra. Post that we will go into calculus.
Uh, Hi, sir. One
Hello.
request is there. Actually, that webinar recording and the actual recording, they are combined in the one folder only. If you
Mhm.
can combine, means we can separate it, it will be easy to access real class recording.
Okay, sure. Definitely, I'll ask the team to do it.
Sure, sir.
Okay. Okay, then let's get started. I think we have enough people, and people will keep joining. So remember, we did determinants last time, and determinant was all based on. Today, you will understand why you studied determinant just before eigen decomposition. What is the essence of it? But remember, determinant was a simple formula broken determinant. Sorry, was simple formula broken into using minors and cofactors and cofactors, right? So I have given you an HTML which clearly explains all of these things. But the idea is simple. Minor is if you're expanding the concept of determinant via a row, let's say you have a 3 cross 3 matrix like this. No matter whatever element are there, let's say you stand here, you remove that row, that column, whatever is left for you, this small 2 cross 2 matrix, this small matrix, the determinant of this small matrix is called as minor. So once you find determinant of this matrix, this 2 cross 2 matrix, that is called as a minor. Okay. And cofactor is written like this: Cij is equals to minus 1 to the power I plus j mij. So it just gives positive or negative value to whatever minor that you have computed. And I gave you the idea. We actually solved a problem. How do we compute determinant? It is quite easy to find out what exactly is determinant using all of these formulas. But obviously, in your examination, first the questions would not be directly based on this. You'll have to understand the intuition of determinant. Determinant is but when the transformation is when transformations are happening, by how much does the volume or area changes. So let's say when you are in two-dimensional space, something like this. Let's say this is your x-axis, this is your y-axis, or second dimension, first dimension, second dimension. Let's say that these are your grid lines. Right. And when the transformation happens, there are chances that these grid lines, it might get shaped like this. Now, when your grid line changes, let's say this is your origin, the area between grid lines, by how much that area between grid line is changing is called as determinant. So let's say by how much the area is scaling. So initially, let's say the area is 1, right now the area is 0.8. So your determinant value would be 0.8. This is the physical realization of what exactly is determinant. Determinant is by how much the area included in the grid lines gets scaled while the transformation is happening. Right? I give you that entire intuition. This is this embeds everything in linear algebra. This entire equation, right? A into x is equals to b. A matrix A getting multiplied to vector x produces a new vector b. Now, because this can only happen when I told you that when you have a rubber sheet of paper, think of your two-dimensional or 2D plane, something like a rubber sheet of paper with all these grid lines. Let's say this is the vector that you have. When you stretch it, something of this sort, your vector would get stretched. It would get to a new point. It will get elongated, right? Now the vector has reached to a new point. When you do some different type of transformation based on how you are stretching it or how you are rotating it, your vector would move to a new position based on all those types of transformation. Linear algebra is the study of these transformations. Now, to understand whether the transformation is actually uh, expanding the space, or the transformation is flipping the space, or the transformation is rotating the space, you will have to understand the value of determinant. If the value of determinant is positive, let's say here, and the value of determinant has got reduced, right, 0.8, it means that whatever transformation is happening, it is causing a squishing effect. The area is getting diminished. When the value of determinant is equals to 16, it means that the area is getting enlarged, or there is a stretching effect which is happening. Right? I told you in that animation, let's say here, I'm just getting started, so I'm giving you a background of what you all went through. So let's say this entire transformation, right? In this particular case, let us say that this is a vector. Now, during the transformation, this entire, let me change it to something else. During the transformation, this entire grid area between the grid lines, that it entirely changes, right? This is how see the vector getting changed or moved to a new position. That vector is that currently outside the entire perspective of what I have drawn, but you are able to see at least this area between the grid lines, right? Now here you see the determinant value. The determinant value is still 1. So which means that whatever is happening, it is not changing the area. There are transformations which are happening, but the area is not changing. But there could be certain transformations like this. Now you see that determinant value is negative. It means that the entire region, the entire space is flipping. You see that flipping action happening, and that's where, mm, see, as soon as it flips, the determinant becomes negative. You see the determinant at the bottom where my cursor is. As soon as the entire region flips, you visualize that the determinant becomes negative. There is no realization other than this that I wanted to help you understand. Right now, we are visualizing two-dimensional space. If it would have been a three-dimensional space, the determinant would have been a volume. Okay. In that case, we would have been discussing about how much the volume changes when this entire transformation happens, right? So determinant is nothing but it gives a perspective of what kind of change is happening. Okay, whether it is flipping this space, whether it is doing some sort of stretching. Let's say, for example, if we have values like this, now you see that the determinant value is 5.97, almost 6, which means that the area is getting scaled up by 6 units. The area can, let's say, a small area like where you see this entire area was 1 unit, right? Where my cursor is. Now, if the area can go up to 5 only when it is the entire square or entire figure that you see in grid lines, it is getting expanded, and that's why the determinant is positive or a very large value, right? So this is the intuition that you need to get, but I'm very certain that you will not obviously not be getting questions directly on determinant to compute determinant. There are very less chances, but if that comes, you will have to use this formula, the same cofactor formula. Okay. So you would, let's say, for example, you have a matrix which has been given like this. Let me solve a problem rather. Let's say you have 1, 2, 3, 1, 2, 3, 0, 0, 1. Okay. Now, in this particular case, if you have to compute the determinant, you can compute the determinant while expanding on any row. So let's say that we have to compute the determinant and we have been restricted to expand via first row. So how would we will be doing that is we will just do wherever our value is, let's say we'll first find the first value of the matrix, which is 1, right? And then our cofactor value, Cij. Now, Cij is firstly you'll find minor. For finding minor, you will remove the first row and first column. So you have got a small matrix which is 2, 3, 0, 1, right? Now, in this particular case, you already know the determinant of this matrix or 2 cross 2 matrix is nothing but AD minus BC, right? So you multiply cross diagonal element and subtract them. So it would be 2 into 1 minus 3 into 0, which would be 2. So herein it would become 1 into 2. Then you will go back to the second value in that row, which is 2. Now the second value in that row is 2. So already have told you that it would be a checkboard pattern, because Cij, if you think of cofactor value, Cij is equals to minus 1 to the power I plus j. Now, as soon as you move to the second value, which is C1, 2, or first row, second column, it becomes minus 1 to the power 1 plus 2, which is nothing but minus 1 to the power 3, which is negative, right? Hence, you will first write negative, whatever value is there in that cell, which is minus 2, and then remove that row and column. So you will eliminate this column, this row, whatever you get. What you are getting is 1, 3, 0, 1. Now you will find determinant of this. Then you will go to the third element, which would be eventually plus 3 by going by this formula, right? It would be plus 3. And the determinant of, let's say, eliminate all of these, you will be getting 1, 2, 0, 0. Now, obviously, the determinant here is would be 0, because if you multiply 1 into 0 minus 2 into 0, it's going to be 0. The determinant in this case would be 2. 1 into 2 is 2, minus 2 into 1 is what? What? 1 minus 0. So basically, the determinant is 2 minus 2, which is 0. Now, eventually, you already know that determinant would be 0, because if you see here, the matrix that I had considered, the matrix was this. I mean, I intentionally considered this matrix 1, 2, 3, 1, 2, 3, 0, 0, 1. Now, if you see row number 1 and row number 2, they're the same rows, right? If you have dependent rows, or let's say if you have same rows repeated in a matrix, then determinant would always be 0. Similarly, if you have repeated columns, if you see here 1, 1, 0, 2, 2, 0, it are nothing but the second column vector is nothing but scaled version of the first one. If you have a situation like this, your determinant would always be 0. Okay. Now you can also get to from here, you can also get to a point that in this case, what is the rank? If I ask you, what is the rank of the matrix? What could be the maximum rank of this matrix? Where are you? Two, right?
One, one.
Maximum. One or two, maybe one or two. Anything. Maximum rank can be two. But there are chances that if the third vector is also dependent on a also dependent vector, in that case, the rank would be one. Otherwise, in this case, right now, as far as I can see, it could be two. Okay, because the rank is two, matrix was 3 cross 3. There were three row vectors, three column vectors, but rank is 2. Now, for an n cross n matrix, okay, for a n cross n matrix would only have rank n if its determinant is not 0. You get this idea, right? Right now, you just saw that this was a 3 cross 3 matrix. By logic, maximum rank of this matrix would have been 3. But because there are dependent rows and columns, you are saying that rank is 2 because there are only two unique information that you have, right? Now, you also found that in that particular case, determinant was also 0. In this case, determinant was 0. So, for a matrix to have a full rank as in if you have n cross n matrix, its full rank would be n. Full rank would be n. So to a matrix to have a full rank, you need to have this condition: determinant of that matrix need not be 0. Because if determinant is 0, then there are dependent rows, dependent columns, there are dependent equations. Hence, you will never have a full rank of n. This is an important thing to remember. This is what you will also use later on. Okay, but eventually there are two other things that I would want to tell you. There are two other intuitions. First, determinants are always calculated for square matrices, are always calculated for square matrices. Why do you think it is we have this sort of a restriction? Any idea that anyone has? Anything that you feel is making the restriction for determinants to be computed only for a square matrix? Why can't we have determinant for a matrix like this? 2, 1, 0, 3, 1, 2. It's a 3 cross 2 matrix, right? Why can't we find a determinant for a 3 cross 2 matrix? Why do we have to always find a determinant for either for a 4 cross 4 matrix or a 2 cross 2 matrix? Basically, a square matrix, right? Why do we have to lay down this assumption that on not assumption actually, this is not an assumption. This is the overall rule that you have, and the matrix has to be a square matrix for finding the determinant. Why do you think it is such? Any idea that anyone has?
Yeah, sir. So for rectangular matrix, either like one column or row, would we can consider it zero, and determinant would always be zero.
No.
Like, okay.
An
Mm,
idea which I have is because determinants is dependent on the area that is scaled, and area
mhm.
would be found only using square matrices.
Right. That is conceptually getting closer to that, but area can also be there in the cases of because let's say when you have this particular vector, it's basically if you look into a row vector, these row vectors are two-dimensional. The column vectors are three-dimensional. Now the problem with these types of matrices is, remember that it is when you have a 3 cross 3 matrix. 3 cross 3 matrix essentially says that the place where the matrix is, it's a three-dimensional space, right? It's a 3D space. Now we are looking into a volume in a 3D space, basically, essentially speaking, right? So we are looking into a volume like this. So eventually, when you have, let's say, when you are looking into a matrix like 3 cross 2, let's say that we have a matrix of 3 cross 2. When you multiply it with a vector, let's say 2 cross 1, what do you eventually get? What do you eventually? It's
3
a
cross
Adding a
1.
3 cross
dimension.
1.
3 cross
3
1.
cross 1 vector, right?
Three
Or
cross one.
let's say, exactly, when you have a matrix of 2 cross 3, let's say, and you multiply it with 3 cross 1 vector, you eventually what would get? You would get 2 cross 1 vector output, right? Now, in this particular case, you are either adding a new dimension, let's say, or you are reducing a new dimension. Here, the vectors are all two-dimensional. Okay. Here, the vectors are all three-dimensional, right? All of these rows are basically three-dimensional vectors because there are three dimensions. They are getting to a situation wherein the vectors are getting reduced or their dimensions are getting reduced, right? So if you think of just for the sake of understanding, any matrix which is 2 cross 3, it would basically either, or let's say 3 cross 2, any matrix which is n cross m, it is basically saying that your input area, whatever it is, your area is getting changed into a higher dimension or a lower dimension. So if you are having a volume, you are going into an area because the entire area is flattening. Or just, am I audible?
Yes.
Yeah,
Yes,
audible.
sir.
My light went off. I thought the internet is also off. Sorry. So basically, volume is getting changed into area. Now it's not about volume scaling because determinant is how much time the volume scales or by how much time the area scales. You are staying to the same volume or area until your entire space itself is, let's say you start with two-dimensional. After the transformation, you still are having a two-dimensional, just like you are having a transformation like this. Let's say you have a handkerchief and you just have rotated it like this or done some transformation like that. Your input space was two-dimensional, output is still two-dimensional, right? So in this case, you can see how by how much the area between grid lines is changing. When you have a three-dimensional space, you can actually visualize by how much the volume is changing, because you are mapping from three-dimensional to three-dimensional. But when you have a matrix of R n cross m, it's a mapping from n dimensional to m dimension. Okay, or when you have a matrix of m cross n, you have a mapping from m dimensional to n dimensional. So basically, your entire either uh, your dimensions are getting diminished or it is getting enriched. So either you are moving to a higher dimension or you are getting to a lower dimension. Hence, the concept of area and volume is all gone, right? So you don't have, you cannot compare a area which is in lower dimension, compare it with, and whatsoever happens to that in higher dimension, you cannot do that. But anyways, remember that determinants are always for calculate for a square matrix. Okay.
Sir,
Now
sir,
in your slide,
I have one question. Sorry to cut
yeah,
you. Sorry for that.
yeah,
If
no.
you go back, you know,
Mhm.
to the volume, just you explained that, the PDF, the note here. So volume 2D to 2D increase is the determinant, right? If you scroll down,
Yes.
you also explained that if a smaller volume can, like, is there not possibility that, of 3D increases in 3D mode, like volume increases in more volume, so the delta volume will be not called as determinant?
No, if the volume increases, think of it. You
Mhm,
are you are in a 3D space.
mhm.
Your space is getting stretched.
Okay.
So let's say, for example, you have a box, you just have expanded the box. The volume has
Mhm.
increased. Now you know
Okay.
that the volume has increased, that is the determinant value. But let's say now you are expanding the box, somehow the box has become four-dimensional. How would you calculate the volume in that case? I mean,
Oh, so in non-square matrix, there is chances that the dimension can also increase from 3D to 4D.
yes, yes. Dimension can either increase or it can also decrease. So that's why I gave you two of these example. In this particular case, the dimensions are actually, if you think of in any of those cases, there are chances that dimension. Let's say in this particular case, the vector that you are getting, it is this column vector. It is one particular point which has three values. Okay. Now, initially, you were starting with the vector, let's say here, and the vector was having only two value. The dimension was only two, right? Two cross one vector. Now you have enriched it into three. So you basically have moved, your initial vector was 2, 1. Now after getting multiplying to a three cross two matrix, your vector has become 2, 1, 4. You get this intuition now. Automatically you have a new dimension coming up, or
So you cannot.
added up, right? So your vector has moved from two-dimensional to a three-dimensional world.
Yeah. So you cannot determine the actual movement between
Right,
cross time
exactly,
dimension, right? Okay.
exactly.
Okay. Thank you.
But anyways, that was irrelevant because this is just for intuition I was telling you. Okay, now there is on your
So,
slide. Yeah.
just one quick question.
Mhm.
If you see visualization like volume or square, then it's easy to understand that okay, it should be same, right? If it's a volume should be volume. If it's a square, and it should be a. But if you take a 3 by 3 matrix and multiply with a 3 by 1 matrix, then okay,
Mhm.
automatically it will reduce the and it's a square matrix 3 by 3 and into 3 by 1.
So think of it. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, and 3, 1, 4. This is the vector. When you multiply it, what you will be getting? You will be getting three numbers A, B, C. Because it's a 3 cross 3 matrix, it's a 3 cross 1. The output would always be 3 cross 1. Initially, you had three components. Now also you have three components. So basically, your vector which was residing in three dimensional is residing in three dimensional. It is just that it has been transformed. The input space is not changing,
Okay, okay, okay,
right?
okay. Got it.
Okay. Anyways, now on your slide, there are three, four important things which have been given. This is the first one, which eventually we just saw. N cross on matrix, N cross N matrix A has rank n if and only if its determinant is not equals to 0. Now this is important. This is also visually also is very important, because think of what would happen when, in what cases the determinant would be 0, in what cases the determinant can become 0.
If
Just
the space
try
collapses to a lower dimension.
right, exactly. When you are moving from a higher dimension to a lower dimension, think of it as your vector space is, or let's say your vector size in 3 dimension, and you are having 3 cross 3 matrix. You're multiplying it with something like let's say some vector, 3 cross 1 vector. There are 3 elements to it. Eventually what you are getting is, you are getting a 0 vector. Now in this particular case, let's say a into x is becoming 0. So basically x is getting transformed to origin, and this can perfectly happen, right? So if you have certain cases, now when that vector is getting to 0, the entire space is getting collapsed. If you think of it, the entire space, the two-dimensional space that you have, this entire space is getting collapsed to 0, right? And that's why the entire vector, the vector wherever that vector was, let's say the vector was this, but this vector, its length, everything can become 0 when this entire two-dimensional world collapses into a point. And that collapsing in space-time thing, you might have learned or read about things called singularity, right? When the collapsing things happen, right? So in this particular case, your entire space collapses into a point, into an origin. So when your transformation, let's say you have 3 dimensional space in the beginning, your entire space is getting transformed either to 2 dimension, or your space is getting transformed to 1 dimension, or your space is getting transformed to 0 dimension. In that case, your determinant would always be 0, because your concept of determinant is getting changed. If you think about, because here in, let's say you are having 3 dimensional input, you are looking, determinant is a volume here, it is getting changed to 2 dimension. Now determinant is volume is getting changed to a square, or something of like a rectangle. You do not have volume scaling, hence determinant is 0. Here in, it is getting changed to 1 dimension. Think of uh, a cubicle box. You expand it enough such that it becomes a line. You just have a 3 dimension. Let's say you have not like that. Let's say, for example, you have a spherical rod, right? You extend it enough such that it becomes only 1 dimensional. In that case, you are changing 3 dimensional to 1 dimension, right? So the entire concept of volume then goes away. So when that can happen again, that can only happen when, let's say, for example, you have a 3 cross 3 matrix, and you have a matrix like this: 3, 6, 9, 9, 18, 27, 4, 1, 5. Now in this particular case, obviously first and second row are dependent, because second row is nothing but thrice of the first row, right? And hence you have only two vectors which basically could be independent. So the maximum rank that you can have is 2. Now, because the rank should have been, the full rank should have been 3. Now, the rank of the matrix is 2. In this particular cases, when you have dependent rows or dependent columns, the determinant would always be 0. And eventually you will see that this matrix that you see, it basically transforms the vectors into a 2 dimensional space. Okay, that's what you would be seeing, and that's why I told you. Remember, in the very first class, I told you what is rank. Rank is the dimension of the output space while the transformation is happening. And AX is equals to B, and some sort of transformation that matrix A does. When after the transformation, let's say you start from a 2 dimensional space. After the transformation, you are only left with a 1 dimensional space. So rank in that case is 1. So that's the entire intuition, which is what they are trying to prove in different way, obviously it would be difficult. And also, I'll not go through it because this is almost irrelevant from the point of understanding. You just need to understand the intuition. Okay, good. Now this is
In
the
exam, will
other.
we get the theorem proof as well?
No, no, definitely not. Now this is the other side of it. If determinant is not equals to 0, A has full rank. I mean, both the things are almost, if the other side of looking at it, if determinant is not equals to 0, then you have full rank. I mean, your rank would be, if you are having a n cross n matrix, the rank would be n in that case. That's all. I mean, that's a simple intuition. If you think about it, you have you have s- a these types of transformation. Let's say when your matrix does all the transformation such that the space collapses. Right now, you see that the space collapsed. I mean, it has almost collapsed to a one dimensional. You had a two-dimensional space, but right now the space has collapsed. The reason for that, think of why the space has collapsed. See these values: 2.5, almost 1, 2.5, almost 1, right? So in your rows, you have 2.51, 2.51. The first row is 2.51, the second row is 2.51, because you both the rows are same, and that is a transformation, that is the kind of transformation this matrix is doing, and that's what you are able to see here. Oh, just let me be there. I'm not able to exactly get to the that point, but anyways, you are able to understand that, right now. Now you see that the entire space has collapsed to one dimension. The reason for that is your matrix values of your matrices are actually dependent on each other. The row vector, which is 2.51, first row vector is exactly same as the second row vector, right? So your entire space has collapsed like this, and hence determinant has become 0. And that's what was written down here. If your determinant is non-zero, if your determinant in this particular case, obviously, let's say for example, whatever is written down here, if you think of, again, let's say 2.51 and 2.51, both the rows are same, right? So rank would be 1. Rank is 1, it means that the output dimension is getting one dimensional, and that's what you are seeing here. Your input space was two dimensional, but the input space is getting transformed like this. Your input space was this, but right now it is getting let me play it down, it would be much better. It is getting transformed into one dimensional space, and hence the concept of determinant is gone. Determinant is 0 right now, right? So that's what has been written down there. I hope you are getting that point. Determinant would not be 0 in that case. If determinant is not 0, then A would have its full rank. So let's say in these particular cases, the determinant is not 0, it has full rank. Rank would be 2 because the input space was two dimensional. The output space is also two dimensional, no matter how you transform the space, right? Unless until you make it actually become a line. Now you see that input space, which was the grid, and the output space is this. There are cases, there are these types of matrices which would actually make that happen. Okay, good. Yes, no.
Got it, sir.
Okay. Now this would get us to something more, much more important, and much more, uh, I would say, from machine learning point of view, something that you should be studying. But before getting to that, let me give you, we remember that, let me give you a simple perspective. Remember that we started with this simple intuition. Ax is equals to b. A vector x getting multiplied to matrix A is getting to a new point B. I told you in that class, you can also think about that matrix A is just shifting or applying some force to to basically transform x to b. So in this particular case, let's say this is x, it is getting multiplied to a matrix reaching to b, and you can easily visualize this. Let's say 1 2 0 4. Now if you multiply this, let's say this is 1 2 vector. Okay. Then eventually what you'll be getting is 1 times 1 plus 2 times 2, which is 1 plus 4, 5, and 0 times 1 plus 4 times 2, which is 8. So you are getting to a new point. Let's say that the second vector is not written or not shown correctly. Let me show it now. Let's say it is getting to a new point, which is 5, 8. Then that's what you see, right? So this matrix basically is transforming this vector to a new point, or in a way you can think of it is applying some force on this vector such that it gets to a new position. Now when we discuss about force, we also know that force has certain direction, right? So eigenvectors are those principal axes or principal direction of forces. Now, to understand all of that, I will go into the mathematical details and we'll solve a problem. Those are the kind of problems, again, saying this is one of the most important topics, which eventually is asked either in regular or makeup. People who are appearing for makeup, if they are lucky, you will be asked about the problems. And from eigenvector, if it is asked in regular, people might get, or let's say, for example, the contents that we are studying right now, eigen decomposition, in the next lecture, singular value decomposition. One of them would be asked in, obviously, questions from one of them would be in regular exam and one would be in makeup exam. Maybe, I don't know which one would be what, but there are chances that you would get one question from eigen decomposition in your exam, and or if you are being asked eigen decomposition, you will not have singular value decomposition, obviously. So these two topics are very important. But getting to your core intuition, you have understood the point that the vector x is getting transformed to b. Now, eigenvectors are special directions. Think of this vector is getting pushed to new point. There could have been certain vectors which are not getting pushed to the point because of this matrix. This matrix is doing some sort of transformation, but this matrix might might not push the vector to a new point in such a way that the vectors are getting to a new point, but they are not losing their axes. For example, let's say if I have a vector 1, 2, after getting multiplied to a matrix, it is only getting to a new point, which is, let's say, 4, 8. Let's say that this is the point. Now, 4, it is this point. What is happening? 1, 2 vector is only getting multiplied to 4 and it is getting shifted to 4 and 8, right? So basically, there are cases when a matrix A, when getting multiplied to vector x, just scales the vector to a new position, and that scaling, for example, is called as eigenvalue. So for example, herein I am not writing ax is equals to b. Instead of that, I am just saying that x is not becoming b. X is becoming its own scaled version. Ax is equals to lambda x, which means that x is getting to a new point, but that new point is dependent on, let's say x is getting to a new point, but that new point is dependent on what that scaling factor is. And this scaling factor is called as eigenvalue. Okay. Now, to help you visualize this, think of it as you have a vector here. Now, after getting multiplied to a matrix A, it is just getting stretched to a new point. So let's say that this is 1, 1. Okay. It is getting to a new point 2, 2. Now, this vector is just getting scaled by 2 units, right? 1, 1 is getting scaled by 2 units. So you can write like this as well. A into x is your 1, 1 vector, is equals to 2 into x. This is the core equation of eigenvectors. This is basically the equation that you need. Ax is equals to lambda x. So while A transform the space, there are certain vectors, or there could be certain vectors. There are chances that there are no vectors as well. There are certain vectors which don't lose their axis. They stay on their axis while the transformation is happening. Those vectors are called as eigenvectors. And by the value they are getting scaled is called as their eigenvalue. So this is an eigenvector. 1, 1 is an eigenvector. Similarly, 2t, any vector which will be on this axis, which will be called as an eigenvector of the matrix A. Okay, so all the vectors which fall on this axis will always be called as the eigenvector of matrix A. Now, this is, there could be infinite vectors, right? Because let's say there could be 4, 4, minus 4, 4, minus 1, 1, minus 6, 6. All of these are scaled. Let's say if I multiply it with minus 6, 1, 1 with minus 6, it would be just minus 6 and minus 6, right? The vector would be this. It would be somewhere here if you think of, right? At this particular point. But it's still it's on the same axis. Now there could be infinite vectors which after getting multiplied to matrix A, they are on the same axis. So this entire space and on which the all the eigenvectors reside, this space is called as eigenspace. Again, going back to the intuition and idea, or firstly intuition, we started our first lecture with the idea that Ax is equals to B. A transform any vector. A basically is kind of having superpowers. It does transforms X to a new point B. So a vector is moving to a new position. Now there are chances, let's say in our entire grid, there are chances that, let's say this is my entire grid, right? So every single vector, every single point, let's say this is the grid that we have. Let's say that this is the grid that we have. So if you think of every single point is a vector here, even every point that you see on that grid, let's say that we only are specifically looking into the points which are a part of this intersection between grid lines. We're just looking into them. Now every point that you see on this would be a vector. But all the points, because of the matrix A, when you multiply any one of these vectors, some vector, let's say this vector would go to a new point here. Let's say that this is the origin. Okay. So this vector is getting to a new point here. Let's say this particular vector might move to a new point here. Similarly, there could be some vectors which will not change their directions during the transformation. And this is what has been visualized here. So if you see eigen decomposition, if you see once the transformation happens, okay, as soon as the transformation happens, there is this vector x which only gets scaled. You're able to see that, right? It's only is getting scaled. The vector was here. It is only getting scaled to a new point. That is called as eigenvector. The vectors which stays on their axis during transformation, those vectors or those set of vectors, they are called as eigenvectors. Now, if you think of, there are two vectors which are actually getting to their same place, okay, or they are not losing their directions. The first vector is this green vector. The second vector is this pink vector. So look at this, right? Both of these vectors or any vector which lie on this pink line and this yellow line, those vectors would always stay on their axis. Those vectors are called as eigenvectors. They never lose their axis, or they never lose their direction to which they are pointing. So they will only get scaled, they will only get elongated or diminished during the transformation. If the eigenvalue is larger or positive, by larger, what I mean is positive. If the eigenvalue is positive, then they will get scaled. If the eigenvalue is negative, they will get diminished. If you see, actually it is small, not negative, but 0.72. That's why the length is getting changed to what it was, or shortening of length is what you are seeing right now, right? Good. Until here, everything is good. Yes, no.
So vectors which have an orientation flip are also eigenvectors, right? Because it's
Vectors
in the
which,
same axis.
uh, I mean, if they are on the same axis, when the orientation is flips, if the
Hmm.
vectors remain on the same axis, at the same point or some elongated position from that on that axis, then yes, they are eigenvectors.
Okay.
So
So the
sir,
value of means the area of eigen space is changing, right?
The area of eigenspace, eigenspace is, think of what is eigenspace. Eigenspace is the space where eigenvectors reside. Right now, the space where eigenvectors resides are, one space is this line, yellow line. The second space is this pink line. So both of them are eigenspaces for our matrix, or for our eigen. Basically, these are the eigenspaces for where our two set of eigenvectors reside, because we have two different types of eigenvectors. One which is in the first quadrant, the second which is in the second quadrant, or let's say all set of vectors which are following the pink line, they are, this pink line is the eigenspace for them, and this yellow line is the eigenspace for them. So the eigenspace is basically the place where all our eigenvectors reside.
Okay.
Sir, one
Sir,
more
it's
Sir,
question.
what is the
scaled
kind of
version.
question we can expect on this?
And that is what I'm coming to next.
Uh,
So we will
Sir,
be
is
getting.
the transformation or is the property of vector that it doesn't change its axis?
It is a property of transformation. It is not property. It is the property of the matrix. By transformation, matrix bring transformation. It is the property of matrix, not the vector, that gets. So think of it as, uh, there. You already know that a matrix would have its null space, right?
Yes, yes,
Same
yes.
as a matrix has its eigenspace as well. So there are many different spaces that the matrix has: row space, column space, null space, and eigenspace. Row space is where all the linear combination of row vectors is. Column space is that the combination of your all columns are. Null space is if your matrix has certain set of vectors which are getting pushed to zero, they are called as null space. And let's say, for example, if you have any vector which is here on this pink line, if after getting multiplied to the matrix it is getting to zero, then this entire set of vector which lie on the pink line would be the null space line. This is the this would act as a null space line. Right now, the all the set of vectors which are following on the yellow and pink line, they are eigenvectors because they are not changing their orientation while, or let's say they are not changing their axis while the transformation is happening. Right. So those are the eigenspaces. Those two are the eigenspaces right now for our two-dimensional matrix A.
Sir, one
Okay,
last
sir.
thing is that it's all depend on the force which is getting applied on the vector, which is the matrix, right? How good is
Right.
the matrix is, right? It is not about
Right.
the vector, right?
It is not
Now,
about the vector. Yeah.
vector, yeah. So, does a matrix should be only on 2D? Like, is there any special type of matrices should exist in a particular characteristic to have a eigen space, or like can, like my question is, will 3D will also work in such manner, or like
Yes, yes, yes. Let's say there's a matrix 2 1 3 1 4 1 0 minus 1 2. Let's say that this is the matrix. And in this matrix, there are chances that you will get three different eigenspaces. Or let's say you can even get an eigenspace which is two-dimensional, and another eigenspace which is one-dimensional. Okay. So right now we were only looking into 2 cross 2 matrix, let's say 1 2 2 1. In this particular case, we were looking into eigenvalues. There would be two. In this particular case, there can be maximum eigenvectors could be two. There are chances that both the eigenvectors actually lie on the same axis, but there could be eigenvector 1 and eigenvector 2. Now eigenvector 1, wherever that eigenvector 1 lies, let's say for example this is the vector, all the vectors which lie on the same direction, they are also eigenvectors. It's not like this is the only eigenvector. So all the eigenvectors which are a scaled version of this would be an eigenspace. Similarly, this would have its own eigenspace. Let's say there are chances that if both of them are same, then the eigenspace would be the same. If both of them are different, then the eigenspace would be different. But now think of from 3D perspective. If you have a 3D space and And because if you have a 3D, let's say, in that case, there are vectors which, let's say, for example, this is one vector and this is the second vector. Okay, there are chances that um, all the three vectors lie on the same coplanar. They are all pointing the same direction. So or everything, because it's a 3D, right? Everything that this could be a plane looking like this. So every vector that lie on that plane, okay, and on that plane would be an eigenspace for them. So this the eigenspace in this particular case would be a two-dimensional space, could be. An eigenspace could be a one-dimensional space as well. So there are cases that can happen, but generally you would see that the eigenspace could be a two-dimensional. In 2D it could be a two-dimensional space like a line. In three-dimensional space it could be a two-dimensional space like a plane. And those are the situations that can exist, and it can also be a situation like in a 3D you can have a 2D eigenspace, or in a 3D you can have a 1D eigenspace. Both of them are possible.
Yes, so 1D is quite easy to understand when you say, same axis, right? Either. But in case of an 2D eigenspace,
It
you
is
are
difficult to visualize, but
okay. Okay.
think of it, you have this plane, okay,
Mm.
the vectors are on the same plane. Any vector that lie on the same plane, they would be the eigenvectors.
It is not about axis. It can be a plane as well, and all
Yeah,
vectors.
so think
Oh,
of it as
okay.
this entire plane right now. This entire plane is getting stretched.
Because of the transfer
Transformation.
force of applied by
Transformation.
3D
Right. 3D
matrix. Oh,
matrix.
okay.
Right.
So all point in
All
this
vectors,
space.
yes, in this space,
All,
they are the eigenvectors in that case.
okay. Okay. Thank you, sir. Thank you. Thanks a lot.
Now the kind of questions which will be asked in your exam, this is what is most
Sir,
important.
one
Yeah.
question. Sir, so the eigenvectors and the null space both will be same for a matrix?
No, I will tell you about it, and we are getting into that direction.
Okay.
Okay. Now think of how can you solve, how would you, let's say there is a question which has been given. Let's frame a question which is slightly easier to solve. Obviously you'll be solving a different question. Not different, but slightly difficult question. Let me frame question with zero value so that I don't have to do a lot of calculation. I'm just showing it to you to avoid calculation. Okay, that's why I'm considering these some of these rows as zero, but you might not get a question wherein the rows are zero. There are two other properties that I would tell you after this, which are extremely important, and there are cases that I have seen in previous year's examination when the question was fairly simple. People unnecessarily spent or they spent a lot of time solving it via the way I am telling you, but because there are shortcuts. So let's say that there is a 3 cross 3 matrix, which is, let's say this is matrix A, and you have been asked to find out what are the eigenvalues of this matrix. Eigenvalues, what are the eigenvectors? And let's say that someone else has also asked what is the basis of eigenspace. Eigenspace. Let's say that these are the three questions that you have. One, two, three. And there are chances that you might get a very simple question to find eigenvalues. Slightly complicating to find eigenvector, much more complicating to find eigenvalues, but we will find all of them for this matrix. Okay, that's the main intuition for this class, because that's the main idea of this class, eigen decomposition. How do you decompose a matrix? But the idea is simple. I'll tell you what this exact idea is. Uh, Keep in mind this question, okay? We'll get back to this question again. I just told you that a matrix A getting multiplied to vector X just scales the vector, right? Now what happens is you can also say that AX minus lambda X. Now this is where someone who had asked the null space question would come in. So ax minus lambda x is equals to 0. This is how I can also write it like. So I can also write it like a minus lambda I into x vector is equals to 0. Why I had to use I here? Any idea? Anyone to give me that answer?
Yeah,
As a
identity
as a
matrix will not
matrix.
Because
change
it's an
in
identity
anything.
matrix
To
and it doesn't
subtract
impact
A to
p-value.
Exactly. A is a matrix. You cannot subtract a scalar number from a matrix. Obviously, you'll have to you can only subtract a matrix from a matrix. Hence, the identity matrix comes in here to help us with that, right? So you can subtract a minus lambda a. This is all looks good. When you have scalar numbers 3 minus 2, it's all simple. But when you have matrix like 2 1 1 3 minus 2, it doesn't make sense to subtract a scalar number from a matrix. Hence, you need 2 into the identity matrix. Okay, this is what that is. Now, this is there are two intuitions about this. First, there all the direction of x, those are eigenspace. You have got that idea. But think of what is exactly here. Let's say that if I write a minus lambda I as m, so we are just saying m into x is equals to 0. And what is this? What are these set of equations are called as?
Null.
null space.
Null
Null
matrix.
space.
Null matrix.
Homogeneous, right?
Homogeneous.
Right, right. And uh, this is the null space of this vector x. The direction of vector x is the null space, right? M into x. So basically, a minus lambda I is a null space, okay? And x vector, the direction of x vector is the eigenspace, okay? So both are two different things. The answer to that is null space is not the eigenspace. Okay, eigenspace is constituted by the matrix A minus lambda I. But anyway, how do you why this is important? Now we have gone to a place wherein I'm saying A minus lambda I times x is equals to 0. Now to solve this, we generally or to actually make it really easy to solve problems, what we eventually go to is we say that either we can solve like this, or we can directly say determinant of a minus lambda I is equals to 0. And this is why we studied determinant just before eigenvalue decomposition. Now tell me, because of all the intuition that you have had since lecture 1, how in the world this second statement that I have written, where does determinant comes in from? Why I am writing that a minus lambda I into x is equivalent to determinant of a minus lambda I is equals to 0. Why would I write it like this? A minus determinant of a minus lambda I is equals to 0.
Matrix
Because
has to collapse.
when you will
Exactly.
transform
Who
3D to
said that?
2D, yes, sir.
The matrix is collapsing. Think. Let's say the not matrix, but the input space is collapsing. See here, mx is equals to 0, right? So basically, a minus lambda I into x is equals to 0. If the vector is getting to 0, it means that the entire space, the two-dimensional space, let's say this was the x vector, this entire space is getting collapsed to a point. When the space gets collapsed to a point, the concept of determinant is not at all there, right? Hence, determinant would be 0. And that's why we write it as determinant. Most of the people uh, that you will see who teaches this concept, they go by first teaching characteristic equation and so on, and then they abruptly use this determinant of a minus lambda is equals to 0. No one, most of the linear algebra teachers would just tell you that this is how it is solved. The intuition about it is the entire space is getting collapsed. Hence, determinant is equals to 0. Okay. So
So
basically
here,
area. Yeah, go
So,
ahead.
so
so
thank you,
sorry.
sir, for explaining determinant first and then using it. Thank you. Thanks a lot. Yep.
any dimension of matrix has to be has to collapse, right? Because
Right,
the
exactly,
vector is
exactly.
always one. I mean, singular,
Hmm,
single
hmm.
dimension.
Right, right. So now the other thing is, because you have this equation determinant of a minus lambda is equals to 0. Now we will feed this idea to solving this question that we had. Where is that question? This question. Okay, let's solve this. So what did I write? I had written determinant of a minus lambda I is equals to 0. So we will first constitute a minus lambda I. So we have 2 0 0 0 0 3 1 1 3. A, this is A, and then you have lambda. What would be I? Identity would be 3 cross 3 matrix, which would have diagonal element as 1. Above it, below it, everything is 0, right? So you would have 0 0 0. Now you have A minus lambda I. This is your A minus lambda I. Let's first give it some form. So basically your matrix eventually would become 2 minus lambda, right? 0 0 0 0. 3 minus lambda, 1 1, and here 3 minus lambda. So this is your A minus lambda I, right? Now you have to find out determinant of this matrix to find eigenvalues. So determinant of this matrix has to be equals to 0, right? Now tell me, how would you find determinant? You already know that to find determinant, it is very easy to expand via first row, right? Because two of the entries are 0. Hence, you can easily, that's that's the reason I took it as 200 to eliminate the kind of calculation that I had to do. But now we'll find the determinant of a minus lambda I, which eventually is basically the first element 2 minus lambda. Okay, and then you would have the 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 minor. The minor would be of this matrix, which is 3 minus lambda, sorry, 3 minus lambda, 1, 1, and 3 minus lambda. Now you will have the second element, which is 0 into the matrix. Doesn't make sense because the element is 0. Third element 0 into the matrix, or determinant of that matrix, which would be 0. So basically it is 2 minus lambda into determinant of this matrix, 3 minus lambda, 1, 1, 3 minus lambda. So this is what you will have to find out. And what it would be eventually. So it would become like this: 2 minus lambda, 3 minus lambda into 3 minus lambda, which would become 3 minus lambda square, right? Minus 1. So this is what it is. Now it would be 2 minus lambda. If we expand this entire thing, what it would be? 3 minus lambda. I'm just thinking of a square minus b square, not like that. A
But
minus b plus a plus b, right? So 3
but
minus
it's not
lambda
3
minus 1.
minus lambda. It is 2 minus lambda.
lambda minus 4.
Lambda
Right.
minus 4, lambda minus 2.
Yeah.
Yes. Okay.
But
So
there is a missing. So can you scroll up, sir?
yeah.
Instead of 2 minus lambda, you have written 2 minus lambda.
Where?
Okay. Yeah, okay. Sorry. Correct.
Should be right. Okay. So this is basically of the form a square minus b square. That's why I've written a minus b and a plus b, because a square minus b square is equals to a plus b, a minus b, right? So all of us knows that. So that's what it is. Now we are
Why can
expanding.
we
Like,
not
you can
solutionize
open
it
it.
like a minus b's whole
Yeah,
square?
you can open it. That's fine. That's also fine.
Okay.
Just for the sake of making the solution easy. Okay. So this would become 3 minus 1, 2 minus lambda, and 3 plus 1, 4 minus lambda. Now, basically, this is the determinant that you have. What we'll have to do? We'll have to say determinant is equals to 0, basically, which means this is equals to 0. Or we say that 2 minus lambda square into 4 minus lambda is equals to 0, right? Hence, the only values of lambda are 2, and 4. These are your eigenvalues. Good?
So 2 will be plus minus 2 or only 2?
2. You'll get only 2. Okay.
So shouldn't it be 2 comma 2 comma 4?
Yes, it should be 2 comma 2 comma 4. I mean, obviously 2 comma. I have just written there are two unique values 2 and 4, but the eigenvalues are 2, 2 and 4.
So does it make a difference?
It does makes a difference because you have three-dimensional matrix. Then you should have three distinct eigenvalues. Now the distinct eigenvalues are not there. But if you have to write three different eigenvalues, you'll just write 3, 2, 2, 4. I have seen in last semesters people have deducted marks just
थोड़ा
because of
ज्यादा नहीं चाहिए कल जैसे शक्कर कम डालने बोल
Hi, sir. One question on this. The way you solve is really good. The second last, you determine 2 and 4 are the unique values, right? Which is now when you say how to plot this on space, right? So these are the eigen values for that matrix, right? So how you have plot, like how this 2 dot comma 2.4 came? Sorry for this question if it is a
This is
dumb.
slightly difficult for me. I should have taken a 2 cross 2 matrix example. It would have been easier for me to actually visualize. But three-dimensional case, I mean, plotting it is difficult. I can visualize this. I can embed it in my mind what is happening. But thinking of what exactly it would look like on a board which is two-dimensional and representing three-dimensional on a two-dimensional board is very difficult. But what I can do is I can share you a representation of it in HTML so that you can understand it. I'll do
But
that.
yeah, but in exam, so we all understood, we came at this point, right? So
Right.
if so the answer would be 2 comma 2 comma 4, or it will be 2 or 4. I just wanted to understand. So
The answer would
eigen
be 2
value
to 4. There
2
are
to
three
4.
distinct eigenvalues which are 2, 2 to 4. So the answer would be 2, 2, 2 and 2 and 4.
So quick question. Is there any relationship between the, like the number of dimension of the matrix with the number of eigenvalues? Like if we are
Yes.
adding, multiplying the
Right. If
three
you have 3
dimension.
cross 3 dimensional matrix, the number of eigenvalues should be 3. If you have 2 cross 2 matrix, the number of eigenvalues should be 2, the number of eigenvectors. Given that they are distinct, if the eigenvectors are only one, let's say in this particular case, there are both those eigenvalues are same. Now, because the eigenvalues are same, the eigenvector that will be computing next, they will eventually form on the same line. Okay, you will see that the eigenvector would be eventually are the same. The vectors are also same. Okay, because the eigenvectors are same, you would have one dimension coming out of, or let's say one axis coming off out of 2, 2, and one space coming out of 4. I'm just helping you understand in 2 dimension. This is the eigenspace of 2, 2, and this is the eigenspace for 4. That is what you have. Okay, so mm, both the things would be there. There would be only two distinct directions now
So
of eigenvectors.
if direction changes, then it's not an eigen.
Sorry?
If the direction is changing, then it's not eigen.
No, I'm not saying. I'm just saying that because there are two, the lambda 1 value, let's say first eigenvalue is 2, second eigenvalue is 2, third eigenvalue is 4. Okay. Now you will find out what is the eigenvector constituting, or what is the eigenvector corresponding to lambda 1 is equals to 2. But because both of them are same, isn't it both of them would point to the same vector?
So
Yes.
it's just a scalar. It's just the vector is getting stretched.
Right, exactly.
Okay.
So they would point to the same vector. This would point to a different vector. Okay. Now these are these basically, let's say when when I wrote ax is equals to lambda x, you have found the value of lambda, but you haven't found what exactly is that vector x, right? But in this particular case, we have found three distinct values, or actually two distinct values, 2 and 4. Now, to find out eigenvector, what we'll have to do is we'll have to first take the first eigenvalue. So the eigenvalue 1 is equals to 2, or let's say lambda is equals to 2, right? So we'll first solve for a minus, or given that ax is equals to lambda x is what you wrote, and then we found out a minus lambda I into x is equals to 0. Or you can, in this particular case, because you have found lambda, value of lambda is equals to 2, you will just feed in. So it would be a minus 2I into x is equals to 0. Now a minus 2I is what? You will just feed in that value here, right? So this is what a minus lambda I is. A minus 2I would be just feeding in lambda is equals to 2. When you feed lambda is equals to 2, 2 minus 2 would become 0. This 2 minus 2, 3 minus 2 would become 1. This would become 1. So basically the matrix would look like, I'll have to memorize this, 2, 0, 0, 0, 2, 1, 1, 2. This is what it would look like. A minus 2I would be 0, 0, 0, 0, 0, because remember here it was 2 minus lambda, and because lambda itself is 2, hence 2 minus 2 is equals to 0. Here it would be 3 minus 2, which would be 1. Okay, this was already 1. Here in it is 1, again 1. So this is what your a minus 2 lambda would become. Now, because your vector is 3-dimensional, your matrix is 3-dimensional, let's say 3 cross 3, you would have 3 component to the vector x. Just write it as x, y, z is equals to 0, 0, 0. Now, in this is a simple case. If you have to solve this, the 3 different equation that you have, you can easily sense that from second row, you can write it like y plus z is equals to 0. And from the third row as well, you will write y plus z is equals to 0, right? So basically, you will have y plus z is equals to 0 as one equation. And x is a free variable because you do not have a pivot there if you see here, right? So x is a free variable right now. So x is already a free variable. You can write x is equals to x s, which is a free value. And you can, from this equation, you can write y is equals to minus z. Let's say that z is equals to t. Let's say z is equals to t, then y would become minus t, right? Because right now x and y, we are treating them, x is free variable, and we are treating z is also a free variable because you have only one equation which is y plus z is equals to 0. You can treat one of them as free variable out, either y or either z. So if you treat z as free variable, we have taken z is equals to t, hence y would be minus t. You can, now we are parameterizing it. So basically your entire x vector would become s minus t and t. So this is your vector, okay, of this form, because this is the value of x, this is the value of y, this is the value of z, right? Or else you can write it like this as well. So if you think of it, you can write this entire thing as 1 into s plus 0 into t. You can write it as 0 into s plus or minus 1 into t. And you can write the bottom one as 0 into s plus 1 into t. Now you have two different factors, s times 1, 0, 0 plus t times 0 minus 1, 1, right? So this is what it would be. Now this is what your eigenvector is, corresponding to lambda is equals to 2. This is what your eigenvector, this is what basically you'll have to find out. So your eigenvector, or your set of eigenvectors, would be of this form. You feed in any value of s and t, you will get a new combination, a new vector. So any, let's say if your s is 2, 1, 0, 0, and let's say t is 1, okay, 0 minus 1, 1. If you add them all together, it would become, let's say, 2 plus 0, that would be 2. And then here it's all minus 1 and 1. So this is an eigenvector 2 minus 1 1. This is the eigenvector. This is one of the eigenvector. Now you can change the value of s, you can change the value of t, get as many eigenvectors and eigenvalues. But because it's a three-dimensional vector, it would always be on a plane. Okay, think of it. It would always be on a, or let's say on a, it can be on a line. There are chances that it can be also on a line. But right now you are able to see that you are getting a three-dimensional uh, uh, figure. Let's say when I say a line in a plane, a line in three dimensions is a plane, right? So it would eventually would be a plane itself. So right now you have got this as as sorry, not this. This as the eigenvector of for lambda is equals to 2. Same solution you'll have to find for lambda is equals to 4. Okay, so for lambda is equals to 4, you will have to find its own eigenvector. There are chances that you will be asked about finding eigenvalues and eigenvector, and this is the way how to solve it. Okay. Now the third question, if you remember, I
Can you
asked
scroll
you.
down, please, in
Yeah,
the
yeah,
previous?
I'll come to that. And the third question that I had written down was find the basis of eigenspace. Okay, and this is where I'll just tell you how do you find the basis of eigenspace. Go ahead. Where you were saying or where you
Yeah,
had the
over
problem?
here itself.
Okay, yeah.
So you said where lambda equal to 2s into the vector 1 0 0, and when we substitute it with 2, s is equal to 2, then the vector becomes minus 1 0 0. So where did this minus come from?
Sorry, this is not minus. Sorry. I was just writing this as
Understood. Clear now.
right.
Thank you.
Sorry, I did that mistake. Now,
Just one
now,
question here.
yeah.
Uh, in the question that we had to find out an eigenvector, so we can take any s and t value and then find out one of the eigenvectors.
Yes, one of the eigenvectors. But all the series of eigenvectors would be of this form. And one of those eigenvectors, if you'll have to find one of the eigenvectors, you can just place any value of s and t.
Okay.
Okay. Now, the third question was to find the basis of the eigenspace. Think of these two vectors. Let's say if I'll come back to you, Nilima. So you have s times 1 0 0 plus t times 0 minus 1 1. Now in this particular case, you have s times any vector is of this form, right? Or you can say that these constitute the basis vectors, because any vector is just a combination of these two vectors, right? Any eigenvector is a combination of these two vectors. Hence, the basis would be if you have to find the basis nothing would be, it would be these two vectors only, 1 0 0 and 0 minus 1 1. Because basis, think of basis is what? Basis is minimum number of vectors with which you can explore the entire space. Which space are we talking about? Eigenvectors reside in eigenspace. Okay. Now the eigenspace is dominated by these two vectors, some linear combination of these two vectors. You feed in new values of s and t, you get to new vectors. So any values of s and t will basically be a part of the vectors coming out of them would be a part of the eigenspace. Now, because the eigenspace vectors are getting constituted based on these two basic vectors, these are called as basis vectors, because basis vector mean, the definition of basis vector is minimum number of vectors that we can have to reach any point in that space. And which space are we talking about? Eigenspace. So the basis of eigenspace would be these two vectors itself. That's all you'll have to do, nothing else. I mean, you already have found these two. You just have to write that these two are bases. Okay. And if you are asked about what is the dimension, the dimension would be 2. How many vectors that you have in the basis? The dimension is 2. Good. So
Still, for
this
lambda 4, we might be getting different bases, right?
yes. For lambda is equals to 4, you might be getting a different basis. There are chances that you might get something like this. let's say you might
For this
get
example, then more than two bases exist, right? Then
right. Let's solve it. Let's say that. Let's solve it for a moment, right? Let's say that we solve it for a minus 4i because lambda was 4, a minus 4 lambda I into x is equals to 0. So our matrix, if we remember, it was 2 minus lambda 0 0 0 3 minus lambda 1 0 what it was 1
1 3 minus
1 3
lambda.
minus lambda.
right. Now in this particular case, if we feed 4 lambda is equals to 4, the matrix would become minus 2 0 0 0 minus 1 1 0 1 minus 1. And then because I told you that x vector is three-dimensional, so we'll just say xyz is equals to 0 0 0. Now this is basically saying minus 2x is equals to 0, which basically means that x equals to 0. And from the second line, you can write minus y plus z is equals to 0, or you can say that y is equals to z. And you will also, from the third row, you will also get the same thing. So you are getting minus 2x is equals to 0 and y is equals to z. Okay. Now in this particular case, you can write the vector, let's say you can take z is equals to t, and in that case, because x is from here, you can say x equals to 0, so you can write the vectors as 0 t and t because x is equals to y is equals to t, right? Or else you can just take t common, you will just say 0 1 1. So now in this particular case, your basis is constituted of this vector only. Okay, so the basis is this and dimension would be 1. Good.
okay. Then three bases exist for this example.
For this example, yes, two bases for first eigenspace, one basis for second eigenspace. This is the space found by this vector and this series, let's say 0 1 1. It is going to explore a plane which never has x is 0. So basically it is, think of it, x y z, this is y, this is z. X is 0, it means that you are sticking to this plane, yz plane, right? So basically the eigenspace is all the vectors which lie on this plane, y and z plane.
So will
Because
it be a
x is already
plane
0.
or a line?
Sorry?
Will it be a plane or a line?
Think of it
This
as if you take t is equals to 4. So in that case, it would become 0 4 4. Okay, 0 4 4, let's say is 4 4. Herein it would be, right? Or 0 6 6, here it would be. It actually would be a line, not the entire plane. But this is that, and this is how it would look like, right?
So we'll have two eigenspaces. One is a 2D plane, and another one is a line.
Is a line, exactly, right? That's right.
And so
Good.
2D
You
space is
you have
for
been,
2.
yeah, sorry.
And so
Go ahead,
2D
go.
space is for lambda 2.
For lambda is equals to 2, that's right.
Yes, sir.
This is
So
what you
dimensions should be 3, right? How 2
no
or 2?
dimension. We if the question says find the basis and dimension of eigenspace. If you have to ask about basis and dimension of eigenspace, lambda is equals to 4 has its own eigenspace. So herein the basis would be this and dimension would be 1. Lambda is equals to 2 has its own eigenspace. So here the eigen basis would be constituted of these two vectors and these two vectors, and dimension would be 2. Both are different. Both the the vectors are different, eigenvectors are different. So they would have their own eigenspace.
Okay.
Okay. Good. Yes, no.
Yes, sir.
There are
Yes,
chances
sir.
that
Sir, one question related to that. How these concepts will be helpful for ML, sir? You mentioned that there is a applicability, right, in ML.
yes, yes, yes. There's strong applicability. I mean, every single maths, even in mechanical, people who are from mechanical engineering, I did my mechanical engineering. So people might relate to maximum principal stress strain theory. There are principal stress theory. If you have to find out, let's say if you are applying force onto mm, some tensile force, if you have to find out what is the core force that is being applied on the object, and let's say the force is being applied in various different directions. So the core direction of forces on that object is given by the direction of eigenvectors. First, this is a physical intuition. Second, in machine learning, there are cases, these lambda values are not redundant values that you're finding. Lambda values tell you which space is having maximum stretch. Okay, lambda tells you that. So lambda, if the lambda, let's say if you find for a matrix, let's say that you have a user, same Netflix example that I keep giving. Let's say that there are different types of users. This is user number one, this is user two, and then you have user number 100. And then types of genres that they're watching, genre number one, genre number two, genre number three, and so on, right? So this is user genre matrix that you have. In this particular case, if you have to find out, if you decompose this matrix and find eigenvalues, and somehow you find eigenvalue, one of the eigenvalue of lambda is equals to, let's say 10. The second eigenvalue is, let's say 1. Okay. Third eigenvalue is, let's say that this is 100 cross 100 matrix. Okay, or 100 cross 10 matrix. There are 10 columns. Or basically, when I say 10 columns, you have 10 genres. Let's say action, romance, XYZ, right? So this is G1 is first genre, G2 is second genre, G3 is, and then so on. Now, because this is 100 cross 10 matrix in this particular case, but given that this is a non-square matrix, rectangular matrix, you cannot find eigen decomposition. The problem with eigen decomposition is it only works with a square matrix. Okay, so it only works with a square matrix. If your matrix is 4 cross 4, 100 cross 100, you can do a eigen decomposition. But tell me, in machine learning, will you have a situation like this when you would rarely have a situation wherein the number of users is equals to number of genres. So eigen decomposition has a problem first. But just because you have asked the question how it is relevant, in machine learning, what happens is you would have, let's say that you have 100 cross 100 somehow, 100 cross 100 matrix, 100 users, 100 genres. Now, in that particular case, let's say that your eigenvalues comes down to be like this. First eigenvalues is 10, second is 1, then third is 0.5, and then fourth is, let's say, 0.2, and then so on. Lambda 100 is 0.1, right? So if you're, let's say that your lambda, all your lambdas are very, very small, because some of these your eigenvalues are huge. It means that it also means that some of your features are having more variance. Okay, some of your features are having more variance. So if your one of the eigenvalues is very high and all the other eigenvalues are very small, it means that some of the dimensions are basically the core dimensions, all other dimensions are irrelevant. So in this particular case, if you melt this matrix to just like 100 cross 1, you don't have to even, or else, let's say that, and in other words, let's say that you have three different users, user 1, user 2, user 3, and you are computing their age, experience, and salary. Okay, let's say that whatever their values are, uh, someone with 30 years of age, experience of 10 years, salary as 35 lakhs. Some other one with experience of 35 years, sorry, age of 35 years, experience 15, 55 lakhs, and then so on. Let's say third user, 40 age, 25 years of experience, and let's say 80 lakhs as salary, whatever. I mean, I'm just feeding in these numbers. You are already seeing that there are chances that age and experience could be highly dependent, just like this. If they are highly correlated, linear correlation is a linear correlation, right? I might have already told you, when you say correlation captures how much amount of linear association is between the variable. So let's say you plot age and experience, and you find out that the correlation between age and experience is 0.9. Now both of them are highly dependent variable. Okay. Now in this particular case, these two dimensions can be basically combined into one, because they are very linearly correlated. Okay, when you have high correlation in your matrix, in those cases, your lambda values for the matrix would be very high. Some of the lambda values will be high. Let's say lambda 1 is 10, lambda 2 could be just 0.5, and lambda 3 could be just let's say 0.01. Now you are saying that there are three different directions, eigenspaces, eigenvectors. One direction is having more change, the other directions are just redundant. Now what we do in this case is, you just project. This is what you will be learning in lecture number 12. How do you use this? You will project this data into onto axes, wherein you will just discard. Currently you have 3 cross 3 matrix, but your eigenvalue says that only one direction has most variance. So you will discard the two directions and project all that data onto that direction. So in that case, your matrix would become 3 cross 1, and you will use basically one dimension to build your model. So your dimensions are reducing from 3 to 1. I understand it like this, slightly different example. And this is good that you have asked, whosoever has asked. So think of it as, let's say you have this type of data. Okay, let's say that this is the kind of data that you have. Let's say age and experience. Both of them are plotted like this. Which direction do you think is having more variance in this plot? Which
Both.
direction has more variance? Any specific direction that you can point out?
No, same.
Okay. If I have to point out, for example, this could be the direction where the data is more changing, isn't it? This could be the direction. Let's say, for example, if you see here, let me make it more clear. Okay, let's say that this is the data that you have. Your data is more varying along this direction, isn't it?
Yeah.
Right. And then let's say if the data is like this as well. Okay. Then the second most direction could be this. Now you just are having a situation wherein, let's say 90% of variance is captured is there in this direction. Only 10% variance is in this direction. Why would you care for your model to capture your 10% of variance in this direction? You just would build your model on to this. So let's say you find a new axis Z. This is a new direction, which is nothing but a linear combination of, let's say, alpha times age plus beta times experience. Now think of, let's say one individual is having 30 years of age, and this alpha value is 2. 2 into 30, let's say beta value is 10. 10 times, let's say 10 years of experience. What you are getting, 2 into 30 is 60, 60 plus 100, 160. You started from a point where the point was 30 and 10, your age and experience value. But eventually after linear combination, you are having one value. So let's say your data had age and experience, right? Which the first row was 30 and 10. But as soon as you took a linear combination, which is in the direction of maximum variance, you just captured its value as, rather than using 30 and 10, which are two dimensional and you have to do a lot of compute, you can melt this into one value, this row into one value, which is 160. And how do you get that direction? That direction where maximum variance is happening is via eigenvectors. So eigenvectors helps you reduce dimensions. Eigenvectors would help you decide in your huge amount of data, when you will be building machine learning models, which direction to keep, which direction to discard. And that entirely is dependent on eigenvalues. If some eigenvalues are And remember, every eigenvalue is linked to an eigenvector. An eigenvector is nothing but direction, right? So what you'll be doing is all the data you will be projecting onto that direction where the eigenvalue is most. How do you project, by the way? You just take a dot product, right? So you have a vector direction, you whatever your data point is, you just would take a dot product between them. Your projection would come out to as a value, just like this, what we did here.
So,
Good.
Professor,
Yes, yes.
these eigenvectors are the principal components we say,
Right,
right? Along
exactly,
with this.
exactly. That's right.
Okay.
But you will learn more about it. Remember, I told you eigenvectors decomposition has a prime dis prime, I would say, failure case. They can only work for a square matrix, right? Eigenvalue decomposition can never work for a non-square matrix. In your general machine learning problems, you will have many number of rows, user data, few dimensions. So you will have a long form data just like this. So you will have n cross m matrix wherein n would be generally much, much more than m. So you'll have a data like this, right? When you have a data like this, you cannot do eigen decomposition. In that
So,
case, you will have to learn something else, which is called as singular value decomposition, which we'll be learning tomorrow. Yeah, go ahead.
no, can we multiply this matrix into a transpose and then we get a square matrix and we get
That's
get a
that
covariance, right?
exactly is the idea of singular value decomposition.
Yeah, yeah. Okay. Okay.
Okay. So you will learn about it. But before that, just because we have 15 more minutes, let me give you one different type of problem which might be asked in your exam. Let's say that you know that for a matrix A, the value is lambda. Now, if someone gives you a problem saying that find the eigenvalue of, let me frame something which is, uh, let's say that someone gives you a problem. Let's say if A has an eigenvalue lambda, find the eigenvalues of A square minus 5A plus 6I. Let's say that they give you this problem. Okay. It's when you look at it, let's say in the question, they might give you a question like A has an eigenvalue of lambda, then what would be the eigenvalue of A square minus 5A plus 6I? This is actually a very, very simple problem. Just that it is, it might look difficult because you might not have solved these types of problem. And this is the second type of problem which generally are asked from eigenvalues and angle decomposition. Okay, so what would happen is you can directly say, uh, let's say that if we multiply it with vector x, let's say a square minus 5a plus 6I, and we multiply with the same vector x. So basically what we are saying is a getting multiplied to x just scales that vector. So we know that the eigenvalue for matrix A is lambda. Now we are saying that what does this matrix does to x. Okay, so let's do that solution. In this particular case, we would be having a square x minus 5ax plus 6ix, right? Now, if you think about it, you can write it as a into ax minus 5ax is equals to lambda x. You already know 5 into lambda x ax, because ax is equals to lambda x. That's what you already know, right? Plus 6 into ix, right? Now you can write a into ax is equals to lambda x, right? This becomes 5 lambda x plus 6 ix is x. You can directly write it like this, right? Now you have lambda x, a into lambda x, or you can write it as like lambda into ax, right? Minus 5 into lambda x plus 6x. Or this again becomes lambda x. So you will have lambda square x minus 5 lambda x plus 6x, right? Or you can take x common again. You can say that lambda square minus 5 lambda plus 6 into x. So basically, think of it what we did. A square minus 5a plus 6I into x is what we started with. this has become this form. Or you can say that this matrix getting multiplied to x has this scaling factor. This scaling factor is what? You already know as eigenvalue, right? So the eigenvalue for this the matrix would be lambda square minus 5 lambda plus 6. That's all. Good.
Can you explain this one more time? Sorry for that.
Yeah, no problem. See, there could be questions wherein they can come in and ask, let's say, given that the lambda is an eigenvalue for matrix A, find the eigenvalue of a square minus 5a plus 6i. Okay. Now, you already know that ax is equals to lambda x because a is eigenvalue. Any vector x, it would get scaled like this because lambda is the eigenvalue of a. So you can write it as ax is equals to lambda x. You already know this. Now, what this matrix, this is basically a matrix. If you think of a square is, let's say a is 2 cross 2 matrix, a square would be again a 2 cross 2 matrix, right? 2 cross 2 matrix minus 2 cross 2 matrix plus 2 cross 2 matrix. It is a 2 cross 2 matrix. Basically, this is nothing but a 2 cross 2 matrix. We can call it as Bx, right? You just need to know what B does to this vector x now. What is this? The scaling factor. Scaling factor into x, right? So you just need to know what is that scaling factor that this matrix would be doing. Now, I just wrote it in this form, B into X. B is that matrix and X. And because I already knew that Ax is equals to lambda X, this is already given, I just used that property. I decomposed a square X as A into Ax. Ax is equals to lambda X already known. This becomes minus 5 lambda X. This we have Ix is basically identity element. If you think about 1001, if you take 2 cross 2 into a vector x1 x2, it's the same vector. You will eventually get the same vector, right? So this is 2 cross 1, this is this is 2 cross 2, this is 2 cross 1. Eventually you will be getting 2 cross 1. You will be getting the same vector because this is identity matrix, and that's why we have taken 6x here. Now this becomes 5 lambda x. This is what we have been carrying 5 lambda, right? This a into x becomes lambda x. Now I just have taken scalar out. Then it becomes a into x. Ax is already lambda x. So this becomes lambda square x. Now we take x common. It becomes lambda square minus 5 lambda plus 6. So basically multiplying this matrix with a vector x is nothing but this scalar value into x. So matrix into x is equal to scalar value into x. That scalar value is this. So basically the eigenvalue is this. Right? Good.
Okay, yeah.
Okay. Now,
So in this case,
One question.
Mhm.
Sorry to interrupt, Santosh here. So I just wanted to understand on this solutions we are getting as part of Lambda. First, we have in previous classes we have particular solution and general solutions, right?
Mhm.
So when we are doing it, Ax equal to B. So
Mhm.
is it in this eigenvectors when we are considering only square matrix? So this x and the b are kind of multiplied of the x so that it is coming in the straight line, and that is the assumption we are taking from the
No, that is
beginning.
not an assumption. We are not taking that assumption. We are just saying that when ax is equals to b happens, there are cases that b could be just a scale form of x. There are some vectors which will never get out of their directions. So there are cases wherein ax would always be lambda x. This is not by assumption. When you are having any sort of transformation of your input space, I remember I told you a matrix is doing some transformation. It is pushing x to b, and when it is pushing is a force would have its direction. The direction of the force, any vector in that direction of the force would never change its axis. So if the force is getting applied in these two directions, let's say this rubber sheet of paper, this would get stretched like this. But think of any vector which is in this diagonal direction, it would only get stretched. its direction would never get changed. So we are saying that there would be certain vectors which will never change their direction. This is by truth. We are not assuming. This is always going to be true. Whatever transformation that you do, let's say for example, if you expand it from all the sides, you apply a force of your on your two-dimensional space, you expand it like this. Now tell me what would be your eigenvector in this case? Which direction? Eigenvector is a direction. What would be the directions? What could be the directions? First
It's
direction would be
all.
this x-axis, right?
Yeah.
The second direction would be this y-axis, because the force is being applied in both the directions. If you apply a force in this way, let's say you have the two-dimensional space and you just apply force like this, and it gets stretched, the two-dimensional space gets stretched like this. What would be the direction of eigenvector? This,
Same.
right? So this would be the direction. Now this is your this is your test.
Yeah.
Now let's say for example you have two-dimensional space. Okay.
चली
Now
गई क्या?
I did some sort of rotation on this. What would be the direction
और
of
चश्मिश
change?
चश्मिश रहते
Let's say I rotate it by
Perpendicular.
45 degrees.
इधर ही घुसी है क्या?
What?
यहाँ पे ना
Who is
नीचे से
Will
आई.
it be a point?
Yes, tell me.
Will it be a point?
Who is
It's
speaking?
a rotational, perpendicular tangent force.
Exactly, because we are talking about two-dimension, and it's a point, it's along the, let's say you have the thumb rule. Think of you are rotating something, you place your thumb. The only way you can rotate your finger is by placing thumb at the top, right? So you're rotating something which is two-dimensional. It would be around the z-axis, and the z-axis in two-dimensional place doesn't make sense. So in the cases of rotation, always remember there are rotation metrics, orthogonal matrices, right? Orthogonal matrices, they always rotate. Uh, the cases when the matrices are rotating, in those cases you will never have an eigenvalue or eigenvector. Whenever the matrices are rotation, let's say these types of matrices, cos theta minus sine theta, cos theta. Let's say that this is the matrix that you have. In this particular case, basically the eventually this is the matrix based on whatever value of theta. This matrix would do some sort of rotation. Okay, and it might rotate your input space like this as well. Okay. Now let's say it has rotated the input space by 45 degrees. Because there is a rotation happening, there is no eigenvector. The only case wherein you will never have an eigenvector is the cases of rotation. Good?
Got it. Thank you.
Okay. Now, I mean, I'll just end up with one specific visualization, which will help you.
Just one question.
Yeah, go ahead.
Maybe a lame question. This is a 2D plane, and like whatever we are rotating. So if I take a line in the z-axis from the center,
It's a just give me a moment. I was tell me about it now.
so if I
It's a
take a
2D plane.
line in the z-axis from the center of the point,
Let's say that this is that somehow.
so this line won't have any transformation.
See, we are looking into two-dimensional space, but our axis of rotation is third dimension. Let's say you are human, you are already living in this two-dimensional space. You will never be able to, even because you don't know about the third dimension. You are trapped in this two-dimensional space. You will never be knowing about that the third dimension exists. So you will never be able to see that the change is happening around the third dimension. Think about the planetary motion. You have read about the Euler's equation, right? E to the power I theta plus whatever is equals to -1, right? This Euler's equation is the equation of planetary motion. we see that the planetary motions keeps happening in a way that there is sun and then everything revolves around it. But when you look into this equation, Euler's equation, you will eventually see that everything is moving towards a particular time, because the time becomes the fourth dimension. And because we uh, time eventually is, this philosophy by the way, or this is science by the way. Time is so much embedded in our three-dimensional world that we cannot, we measure everything with respect to time. Everything has a start and an end. We come to life and we die. Every single thing in this universe has is basically moving towards a particular time, and you already know that there is entropy to it as well. So you see, we generally visualize the planetary motion like this, but planetary motion happens like this, right? So there is a time to it. It started from somewhere, it is going to somewhere, we don't know, because we don't know time. We have the notion of time, we know that it's a four dimension, but the realization is all embedded in within. It's you can just feel its effect. You will, let's say, if you are into two-dimensional space, you are just visualizing that the space is changing, and there is a rotation which is coming. But the rotation is coming because of what? You don't know. You just know that there is a rotation. I mean, this, I didn't wanted to go into it, but anyways. Okay, now there is this thing which I wanted to help you understand, and I'll cover it tomorrow. See this. Uh, you the basis to rank decomposition, or all the models that you are going to learn in your LLMs, large language models, the fine tuning of them, it's all based on low rank decomposition. Rank is what you already have learned about rank in linear algebra, right? So low rank decomposition, all of these types of things is a concept which is what you will be learning tomorrow. But think of this thing called as spectral decomposition. Spectral decomposition says, and I'll just take 5 minutes and tell you about it. This is the last topic of your lecture 4, and you will see in your lecture 4 towards the end they are just saying about this spectral decomposition theorem, which is basically a matrix getting decomposed into three different matrices. Okay, now I'll just give you an idea about it, what exactly it is and why this is very profound idea. And based on this, the singular value decomposition comes in. Okay, so spectral decomposition says if there is a square matrix. Okay, on the kind of square matrices are, you already know that symmetric matrix, right? Wherein A transpose is equals to A. So if you have a symmetric matrix, and these symmetric matrices have different types of superpowers, I would say. So let's say that this is a symmetric matrix, and this is the example that I'll go through maybe tomorrow to help you understand what exactly it does. So let's say there is a symmetric matrix 2 1 1 2. Okay. Now this matrix would do some sort of transformation. Okay. The kind of transformation that this matrix does, just for the sake of understanding it, look at here. 2 1. Let me use 2. It's a 2 and 1. 2 1 1 2. Just say that this is the matrix, right? This is the kind of transformation that this matrix does. But if you have to visualize how does this entire transformation happen, it might be slightly difficult for you to actually understand what it has stretched somehow. But I should have kept it. Let's say that if you have to visualize it, you might see that there is some sort of expansion which is happening, right? Stretching which is happening. But if these types of matrices, when I said they have superpowers, is because when you have a symmetric matrix, that symmetric matrix A can be decomposed into three different types of transformation that it does in the input space. First transformation is your rotation, which is called as Q transpose. Okay. Second is scaling, which is generally written down as like this lambda. And then Q, again rotation. So a matrix can be easily decomposed. A symmetric matrix can be easily decomposed into three different specific type of transformations: rotation, okay, scaling, and then rotation again. Now visualize this concept here. This is what I created yesterday. You have three different dimensions, three different axes of eigenvectors. Okay, red, blue, and purple that you see here. Lambda is equals to 0.1, lambda is equals to 0.5, lambda is equals to 2.0. Okay. Now look into the kind of transformation that this matrix does. Rotation, scaling, rotation. On it. Rotation, scaling, rotation. I mean, going backwards. Rotation, scaling, and again rotation. Now I'll just pause it here. You are able to see, because of rotation, scaling, and rotation, your three-dimensional space has almost got squeezed into the two-dimensional, because one of those axes, lambda is equals to 0.5. See here, one of those eigenvalues is equals to 0.5. Okay, if this eigenvalue would have been almost become 0, this entire space would have got actually compressed into two dimension, something like this. I mean, I don't know whether I have had that. Okay, let me show it to you here. All subspaces, not here. Matrix composition, decomposition. This is the same thing, but 3D transformation is also the same. Yeah, this is on. Let's say, for example, this is the three-dimensional world, right? If the eigenvalue, one of the eigenvalue would have been almost 0, this entire space would have got, the three-dimensional space would have got into two-dimensional space. This would have got transformed into a two-dimensional space. So see how this entire transformation happened. This three-dimensional space have got transformed into a two-dimensional space, because the eigenvalue, and this is what is important from your tomorrow's class point of view. One of the eigenvalue, when I start showing you, everything is all good, well balanced. Every data point, every vector that you see here in this three-dimensional space, it looks all good. One of the eigenvalue is very huge, right? And not very huge, but at least one first and second are comparatively higher than the third one. Because of which the transformation which is happening. Remember, I told you spectral decomposition is only based on the kind of matrices which are symmetric. These symmetric matrices does rotation, scaling, and rotation. So it starts with rotation, scales, and then rotates again. Because of that, see here, your entire one of the direction there is more variance which is there. In one of the direction where lambda value is less, the variance is very less. You see almost it has got compressed like a burger, right? Now think of, your burger would become a chips if lambda would have been 0, right? And that's when the dimension reduce. This is what we'll learn tomorrow. But anyways, I hope you have got some intuition in today's class and also some problem solving. I have a hard stop. I'll not be able to take any questions, but I hope that you have got some idea about these things. Good. We'll take question tomorrow.
Thank you, sir.
Okay.
Thank you, sir.
Okay. Thanks everyone.
Thank you, sir.
Thank you. Thanks
you.
everyone.
Thank you, sir.
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 Thank you everyone.